And if we have any extra time at the end, feel free to ask me some more questions about it. But what we're going to do in this very last section of Cal 2, I know you're all just excited, is we're going to talk about conic sections. Now, conic sections can be described by taking a two-napped cone or a two-sided cone and intersecting it with a plane. So we've done some of them before. If the plane is, say, perpendicular to the axis of the cones, we get just a circle. If it's slanted, we're going to get kind of an elongated circle, which we call an ellipse. If you have a plane that's parallel to the side of the cone, you get just a parabola. And if it cuts both halves, you know, like if it's parallel to the axis of the cones, we're going to get what we call a hyperbola. Now, we can also do points and lines as this, but we're going to concentrate on ellipses, parabolas, and hyperbolas in this section. So you've done parabolas before, yeah? Algebra 2, college algebra. You've definitely done parabolas before, but you may not have ever seen the definition that I'm about to give you. For Calculus 2 definition, what a parabola is it's the set of all points in the plane that are equidistant from a fixed line called the directrix and a fixed point that's not on the line, and that's called the focus. So if you start out with a fixed line called the directrix and a fixed point called the focus, then every point on a parabola will be equidistant from that line and the directrix, or pardon me, from the point and the directrix. Now, this particular one, I think it's a little bit skewed because of the viewing window, but that's just going to tell you that every point, the distance to the focus and the distance to the directrix will be the same. Okay. In general, the equations of parabolas are just like you remember. Y equals ax squared plus bx plus c. It's just that you probably haven't had to find the focus and the directrix before. Now, if you have a focus, or let me put it this way, if you can find the vertex and either the focus or the directrix, you can figure out everything there is to know about a given parabola. Also, if you can find the vertex and this distance. So we say that P is the directed distance. And I use the term directed distance because you could consider P to be negative. But it's going to be the directed distance from vertex to the focus and vertex to the directrix. Okay. Now, what can you tell me about a parabola of this sort based on things you already know? Do you know how to find the vertex of that parabola? I know I'm asking you to pull stuff from Cal 1 or college algebra, but you can do it. Do you agree that the vertex is the highest point or the lowest point on a vertical parabola?
Yes.
Okay, so it's either the maximum or minimum, right? And so that happens when you have a critical value, in other words, when the derivative equals 0. So if you take the derivative, you're going to get 2ax plus b. If you set that equal to 0, you're going to get x is negative b over 2a. So your vertex is going to occur at x equals negative b over 2a, and then whatever you get when you plug that back in. So if this is f of x, then your vertex will be the point negative b over 2a, f of negative b over 2a. Okay. Now, and I think they do this like on page 790 or 91, I can't remember, but somewhere in there. We can also show that the distance p between vertex and focus, or vertex and directrix, is 1 over 4a. Now, from our college algebra or Cal 1 or pre-Cal, whatever, we know that if a is bigger than 0, our parabola opens up. If a is less than 0, our parabola opens down. So these are things that you have done before, all except for the focus and the directrix. As far as finding the vertex, we're good to go. Same way you always did. Now, parabolas enjoy beautiful symmetry. They are symmetric across a line through the vertex that is perpendicular to the directrix. So when you have a vertical parabola, the line of symmetry, or what we call the axis of symmetry, is just going to be x equals negative b over 2a. It's always just the x coordinate of the vertex. Now, on the flip side of that, if you have a parabola or a quadratic function in y, instead of being a parabola that opens up or down, it's going to open sideways. Okay. Still find the vertex the same way, but when you set the derivative equal to 0, you would actually be finding the y coordinate of the vertex. And the x coordinate of the vertex is what you get when you plug that back in. So for example, let's say we have grab some more paper here. Okay. So let's say we have x squared equals negative 4y. Okay, and I ask you to determine the coordinates of the focus. Let's say maybe the vertex and directrix. Okay. Now, before we start doing any of this, we want to put this in what we call standard form. So we want to solve for the non-squared variable. So this would be y equals negative 1/4 x squared. When you put one of these in standard form, or in standard equation form, the coefficient of x squared is going to be a, always. Okay. Now, if you wanted to find the vertex, in this case, there's no b and no c, so b is equal to 0 and c is equal to 0. So the vertex here, negative b over 2a, would be 0 over 2 times negative 1/4, or negative 1/8, which is just 0. And the y coordinate when you plug it in is also 0. So our vertex is 0, 0. Now, what is p? P is going to be 1 over 4a. So that's going to be 1 over 4 times negative 1/4, or 1 over negative 1, which is negative 1. What's the significance of p? Well, P tells you how far you travel along the axis of symmetry away from the vertex to get to the focus. So the vertex on this one is 0, 0. Who can tell me, does this parabola open up or down?
Down.
Down.
Opens down because the coefficient squared term is negative. So now I have something coming down this way. Okay, if this is my vertex, that means I'm going to go 1 unit inside the parabola to get to the focus. So rather than trying to memorize some formula, if this is the point 0, 0 that we found to be the vertex, what would this point be if we moved 1 point down from that?
0, 1.
0, negative 1. Good. That would be your focus. Okay. Now, what about the directrix? Well, the directrix, we're going to start with the vertex and we're going to go the opposite direction, 1 unit, and draw a line. Well, I'm going to miss that point, aren't I? We're going to draw a line through that point that is perpendicular to the axis of symmetry. So the directrix here would just be y equals 1. So our parabola is going to be all points that are equidistant from this point to this line. So if we do, say, this point, distance from the point to the, that looks about the same. So we're going to have a parabola opening down like that. Questions so far? All right. So what if I had y squared equals, I don't know, 16x? This one is going to be opening sideways. And for some weird reason, this particular textbook really likes vertices to be at 0, 0. So most of them will be, just for the record. All right, so this would be x is equal to, well, let's make that a little more fun. Let's make that y squared equals 1 over 16x. So x would be 16y squared. My vertex, the y coordinate of the vertex would be negative b over 2a, which is still 0. Plug that back into the original, you're going to get the x coordinate is also 0. Okay. But remember, you could always take the derivative and set it equal to 0 to find the whichever coordinate is the independent variable. All right. So what will P be this time? P is 1 over 4a. So that's going to be 1 over 4 times 16, or 1 over 64. In this case, since our parabola has a positive coefficient here, this is our a. Positive for horizontal means it opens to the right. So this graph, we're going to start with our vertex at 0. I know it's going to open to the right. Okay. Now, to find the focus, we're going to move 1 over 64 units away from the vertex. So it's going to be really close in there. So if this is the point 0, 0, the focus would be 1 over 64, 0. Notice I changed the x coordinate this time because it was a horizontal movement away from the vertex rather than a vertical movement. So our focus would be the point 1 over 64, 0, and our directrix, we'd move 1 over 64 units the opposite direction, and in this case, my directrix will be a vertical line, and that would be x equals negative 1 over 64. Now, if I asked you for the axis of symmetry, It's always, for us, it'll be a horizontal or vertical line because we're not going to do any parabolas that open on a slant. But if you have the axis of symmetry, it will always be either the horizontal or vertical line that goes through the vertex and the focus. So that in this case would be y equals 0. Whereas up here, our axis of symmetry would have been x equals 0. And anytime your vertex is at the origin, your axis of symmetry is either going to be the x-axis or the y-axis, depending on whether you open up and down or sideways. Questions so far? Are you just wondering when the other shoe's going to drop? Because these are pretty straightforward, yeah?
I was going to ask.
Can you remind me, where are you getting the directrix from?
The directrix is a line that is perpendicular to the axis of symmetry that is p units away from the vertex. So if you counted right to get to the focus, you're going to count left to get to the directrix, and you're going to draw your line through there. So if this was 0, 0, I just moved 1/64 units the other direction.
Gotcha.
Okay. Now, did somebody else have a question also?
Yes, I did.
Okay.
Is there ever going to be a time where the axis of symmetry won't be, at least in this class, where it won't be x equals 0 or y equals 0?
If your vertex is not at the origin, that would be the case. For example, if you had something like this, okay? My vertex, if I take negative b over 2a, that will be negative 3 over 2 times 2, which is negative 3/4. The y coordinate of the vertex is what I get when I plug that back into the original. So what is that? Okay, 9/16 times 2 is 9/8 minus 9/4 minus 4. Oh, goodness. So that is negative 9/8, negative 2 and an 8. No, 1 and an 8, sorry. Negative 5 and an 8. Okay. Double check my arithmetic real quick. If you can, right quick. Yeah, that's what I get the second time around. Okay. So my vertex here is negative 3/4, negative 41/8. Okay. What is P? P is the distance we move away from the vertex to get to the focus and the directrix. P is going to be 1/4a. So in this case, that would be 1/4 times 2, or 1/8. In this case, since A is positive, that particular parabola opens up. Okay. And so let's see, we have a vertex at negative 3/4, negative 41/8. So about here. Okay. So I know that my parabola is going to be doing this. Now, in this particular case, I could quickly find that the y-intercept is 0, -4 to get the width of it. Okay. So I know my parabola is going to do something like this. Okay. Now, what's the focus? The focus is the point. It is always going to be inside the cup of the parabola, or inside the curvature of the parabola, if you want to think of it that way. But it's going to be on the axis of symmetry. which in this case is x equals -3/4. And it'll either be up or down. But since I want it to be inside the bowl of the parabola, I'm going to move 1/8 of a unit up from this point. So since I'm moving on a vertical line, my focus here, the x coordinate would stay the same. And I move 1/8 of a unit up. Now I moved way too far graphically. We're just moving up 1/8 of a unit. If you move 1/8 of a unit up, that'd be -41/8 plus 1/8 is -40/8, which is -5. To find the directrix, we're going to move the opposite direction. So if we had to move up to get to the focus, we're going to move down to get to the directrix and draw that line right there. And so the directrix would be y equals what over 8? The y coordinate of the vertex is -41/8. I moved 1/8 of a unit down, so that would be negative what?
42/8.
-42/8, exactly, or -21/4. So it can move around, just depends on where the vertex is. All right, so let's take a quick break. We will pick back up and start talking about ellipses and hyperbolas at 1:07. All right. Are we ready to look at ellipses, or do you have any questions right now about parabolas? And this is kind of like, you know, what we were talking about earlier with polar graphs and parametric equations. You know, we could conceivably spend a good 2 or 3 weeks on this chapter, but we don't have time. One thing, you know, we find it very useful to go ahead and introduce you guys to the ideas of conic sections, particularly for those of you that are going to go into Calculus 3, because you'll do a lot of graphing in 3 dimensions in Calculus 3, and a lot of the shapes that we take to 3 dimensions are conic sections. Like you might take a parabola and rotate it, you know, around its axis of symmetry or something like that and get what we call a paraboloid, or we might get an ellipsoid or something like that. But you kind of need to know the basics of these shapes that we're talking about. Okay, so an ellipse. An ellipse, on the other hand, is the set of all points in the plane, the sum of whose distances from 2 fixed points called the foci is constant. So for an ellipse, rather than having one focus as we did on the parabola, we actually have 2 foci. Okay, so I'm going to call this F1 and F2. And what that says is if you take any point on this focus, pardon me, on this ellipse, and you take the distance from that point to the first focus and the distance from that point to the second focus, and then you pick another point on that ellipse and take the distance from that point to each focus. If you add this distance to this distance, you're going to get the same as the sum of this distance and this distance. The sum of the distances from any point on the ellipse to the foci is going to be fixed or constant. Okay. Now, when we go through and derive a formula for the equation of an ellipse, what we get is the general form for the equation of an ellipse is x minus h squared over a squared plus y minus k squared over b squared, and that's all equal to 1. This is the general or standard form for the equation of an ellipse centered at h, k. As I mentioned, this particular textbook tends to like to put the center of things, the vertex of a parabola at 0, 0, and it also likes the center of its ellipses mostly to be at 0, 0. So for a lot of them, they'll just tell you that's the case, in which case h and k would be 0. A is the distance.
I have 2 quick questions.
Okay.
Are we still in planar like graph? Like, or is the graph like going from 0 to 2 pi, or are we back to linear?
Well, what do you think? I mean, you see an x and a y.
Oh, I guess back, yeah, because there's no, okay, linear.
Yeah, so it's actually rectangular coordinates. That's an excellent question. We could talk about polar coordinates for conic sections, but we're not going to. All right.
And then my second question, are both focus points the same distance away from each maximum?
They are actually this, it will be symmetric. You know, the foci will be the same distance either side of the center, which will be either side of this point and this, you know, this distance and this distance will be consistent with this distance and this distance, if that's what you're asking.
Yes, could you repeat that one more time though?
We do have beautiful symmetry. In other words, if you have a focus, say here and here, then the distance from this focus to center and the distance from this focus to center will be the same. And the distance from this focus to this end point and this focus to this end point will also be the same.
Okay, that makes sense. So,
okay. Oh, go ahead.
So like say on the right half of that, those two distances aren't necessarily the same then, right?
No, I mean, your focus, depending on where it is, they may be closer to the center, they may be closer to the endpoints of this axis. It just depends.
Okay, but they are the same. They're mirrored versions of each other.
Right. Yes.
Axis.
Yes. Now, if you look at this axis right here, you'll notice that that is longer than this axis. Now, these two axes basically divide your ellipse into 4 equal parts, but well, I thought I did that earlier. This one is going to be longer in this case than this one, because remember, it's an elongated circle, so it's not really, we don't have a radius, so to speak. The longer one is what we call the major axis, and its length is always going to be 2a. Now, the endpoints of the major axis are what we call vertices. Sometimes I just call them the endpoints of the major axis. Okay. How far is it from center to a vertex is always A. A will always be the distance from center to a vertex. Now, the shorter axis goes from this point to this point. That's what we call the minor axis. So this distance right here, that little length right there, is our minor axis. And its length is 2b. So this distance right here is b, and that's how far it is from center to the endpoint of a minor axis. Okay, now, what if A and B were the same size? What would we have?
Perfect circle.
It'd be a circle, right? So some people call a circle kind of a degenerate form of an ellipse, because, you know, if you don't put in the requirement that A is actually bigger than B, then you get just a circle if A is actually equal to B. But in general, other than when we have circles, A will be bigger than B, but it's always going to be bigger than or equal to B. When A is equal to B, we have a circle. Okay. Now, we also have the unit C, and C squared is equal to A squared minus B squared. So what you say? Well, C is the distance from center to a focus. So if our focus was like right here, this distance right here would be C. Your major and minor axes will always be perpendicular to each other, and your focus here and here, both of those will always be inside the ellipse. So if you get this backwards and do A squared plus B squared, you'd have a focus that's outside the ellipse, so you'd know you're wrong. This is the form when your ellipse is horizontal in nature. In other words, the major axis is horizontal. if the a squared, which is the bigger of the two denominators, if that's under the y squared term, then it's going to be taller than it is wide. So when it's a y squared over a squared, we have a taller, skinnier model than when it's x squared over a squared. But the version, I mean, they're similar in nature. It just depends on where the a squared is. Now, how do I know which one's a squared and b squared? A squared is always going to be the bigger of the two. Okay, because once again, if they were equal, we'd have a circle. So a squared, except in the circle version, a squared is always going to be the bigger of the two denominators. And that's when we put it in standard form. Okay. So if we had, for example, something like, oh, well, I thought I had one. Let's do 16y squared plus 49x squared is equal to doggone it, what do I want to make it? $28. No. Let's make it just nice and make it 784 to start. Okay. Before we can figure out all the stuff about my ellipse, I'm going to need to put this in standard form. In other words, put equals 1. So I need to get a 1 over here by itself. So I'm going to divide the whole thing by 784. Now, when you divide 16 by 784, you get 49 in the bottom. 49 over 784 is 1 over 16. Okay. So in this case, how do I know that this is an ellipse and not, say, a parabola?
Is it because you have a squared plus b squared equals c?
We've got a plus in the middle, and both of my variables are squared. Remember, with a parabola, you either have an x squared and a y, or a y squared, but not both, right? So when you have both of them squared, it's either going to be a parabola, I mean, an ellipse, or what we call a hyperbola, which we'll talk about in just a minute. But when it's plus in the middle, we're going to have an ellipse. Okay. In other words, when they're the same sign, equals a plus 1. All right.
Okay. So kind of one off, but what happens when you cube them?
We don't get a conic section.
Okay.
Okay. These are conic sections are going to have quadratics for these particular types of conics. Now, it's not to say that you couldn't get a graph if you have something cubed or whatever, but it won't be one of these.
Okay.
Okay. So what's the center of this ellipse? Well, I don't have anything being subtracted from either x or y. So those h and k would both be zeros. So this would be 0, 0. Where that would change is if like we had y plus 2 quantity squared or x minus 1 quantity squared, something like that. Okay, what's a squared? A squared is always going to be the bigger of those two denominators when you put it in standard form. So a squared is going to be 49 and b squared will be 16. So c squared, which is a squared minus b squared, will be 49 minus 16, or 33. So c will be the square root of 33. Now, here's what I typically do when I'm trying to draw these. I go, okay, my center in this case is at 0, 0. if I let x equal 0, so in other words, just cover up that term, what would be my two possible y values?
Could it be plus or minus the 7, plus or minus 7?
Yeah, that's exactly it. Just y squared equals 49 would be y equals plus or minus 7. Excellent. So I have 2 points on this graph at plus or minus 7 for y and 0 for x. Okay. If I cover up the y term, I would get x equals plus or minus 4. So this particular ellipse is tall and skinny. Or it's taller than it is wide, I should say. And that comes directly from the fact that the larger denominator in our standard form is under the y term. Okay. Now, how long is the major axis? Major axis is always 2a in length. So in this case, it's going to be 2 times 7 or 14, and the length of the minor axis is 2b, which would be 2 times 4, which is 8. So this one's, and you could just count it. I mean, from here to here is the minor axis, from here to here is the major axis. You could just count those units if you wanted to. What would be my vertices? Now remember, vertices are the endpoints of the major axis. So this would be the point 0, 7, and this would be the point 0, negative 7. The endpoints of the minor axis would be 4, 0, and negative 4, 0. And then the other thing we want to find is what are the foci. Okay. Foci are going to be C units away from center. On the major axis. So the major axis, remember, is the longer one. It would be from here to here in this case. So we're going to start at center and we're going to go C units up the major axis and C units down. So the foci in this case would be 0 plus the square root of 33 and 0 minus the square root of 33. Questions? I know there's a lot to these guys, but if you'll just memorize your basic forms and what A, B, and C are, it's really one of the most straightforward sections we've done recently or at all. There's just a lot going on.
The definitions of all of like the major axis, because like you say it, I guess you say it right here, but like are all of these also on the document that you sent out?
The document is the blanks. I mean,
yeah, okay, gotcha.
Yeah. All right, but you'll have the videos, and I did write it down right over there. Or that's okay. The wrong one. There we go.
Yeah, thank you.
You bet. All right, so that's ellipses, and we'll come back and do a variety of some different types of questions too, but I want to make sure that we get the definitions of all of these in. Last one is the hyperbola. The hyperbola is the set of all points in the plane for which the absolute value of the difference of distances from two fixed points, called, once again, the foci, is constant. But rather than adding the distances, we're going to subtract them. The midpoint of the segment between the foci is what we call the center. So basically, it looks like we have two parabolas going back to back, whether they're going up and down or sideways. Okay. Now, notice the major difference in the form of the equation for hyperbolas versus ellipses is the fact that this is a subtraction in the middle. Okay. This version is one that opens sideways. This one opens up and down. Okay. Now, for an ellipse, A always had to be bigger than or equal to B. There's no such constraint between A and B on a hyperbola. A may be bigger than B, less than B, or equal to B. The way you determine which one's A and which one's B is which one's positive. A squared is the denominator under the positive squared term. It will not, so that one's a typo there. So switch that to A squared minus B squared. Okay. Just so we can be consistent, because it really, frankly, doesn't matter what we call them, but okay, that's pretty common. Okay, now when A squared is under the positive squared term, A is still, just like it was for ellipse, A is the distance from center to a vertex. So that would be this distance right here. Okay. B, we'll come back to B. C is the distance from center to a focus. Okay, so if this is center and this is a focus, then this distance right here is C. B is the distance from center to the end point of what we call the conjugate axis. Where'd it go?
Could you say that again? The distance is
I'm writing it down.
For C, the distance from the center to the focus. Is that what you're saying?
Yes. The C is always going to be distance from center to focus, just like it was for the ellipse. And then B will be the distance from the end point of the conjugate axis to center. So this distance right here would be B. Now, some books, some people, depends. For ellipses, you know, we have the major and the minor axes, which is kind of intuitive in that the major is always longer than the minor axis for an ellipse. That's not true for hyperbolas. You know, just depends on what A and B are. But sometimes people call the transverse axis the major axis and the conjugate axis the minor axis. Just depends on who you're talking to. So you could always call this major and minor. Again, just realize that major is not always longer than minor in a hyperbola. Okay, so the center, just like it was for the ellipse, is HK. A is the distance from center to a vertex. C is the distance from center to a focus. B is the distance from center to the endpoint of the conjugate axis. And the way you find C is A squared, or pardon me, C squared is equal to A squared plus B squared. Notice that's different than from an ellipse. For an ellipse, C squared was A squared minus B squared. Now, two things that we have, well, actually it's one thing, but two different parts of it. that we have for a hyperbola that we didn't have for an ellipse is we have slant asymptotes. So remember, slant asymptotes are what your graph gets close to the further you go out to the right or the left. And so to find the slant asymptotes, if the vertex or the center is at 0, 0, your slant asymptotes would just be y equals plus or minus b over a x. Now, if you move the center, so like we have 1, 3 or 2, 5 or something like that, you just replace y with y minus k and x with x minus h, just like you do shifts generally. So it'd be y minus k equals plus or minus b over a times x minus h. I'll try to stick mainly with the ones where the center is at 0, 0, just to save us some time, like on your test or anything like that, because most of the homework problems will be that variety. Okay. And I'll talk, when we go through an example, I'll show you how we get those asymptotes visually as well. All right, so what if we have this one, maybe. Oh, it's x squared. What is the tell that this is a hyperbola rather than an ellipse?
The negative.
The negative, exactly. If one of them's positive and one of them's negative, then we should either get an ellipse or a point or something like that. I mean, not an ellipse, a hyperbola or just a point. But the fact that they're opposite sign, that goes hyperbola. It's already in standard form. The center, since nothing is being subtracted from x and y, inside there, the center is 0, 0. A squared's always under the positive term for a hyperbola, so a squared will be 7. B squared is under the other square of the variable, so b squared will be 5, and c squared will be a squared plus b squared, which will be 12. So a is the square root of 7, b is the square root of 5, and c is the square root of 12, or 2 square roots of 3. Now, before we go on, here's how I kind of remember, does it open up and down or sideways? If I made y equals 0, in other words, closed off that term, I could get that x is plus or minus the square root of 7, which is a real number, right? So let's see. But if I make x equals 0, that would give me y squared equals negative 5, which is not a real number. So I can't make x equals 0. So this guy is not going to have a y-intercept. So it's going to have to open sideways. Or you can just memorize when the x squared term is positive, it opens sideways. Either way will be fine.
Wait, there's no real number for x squared, the square root of x. Say that again.
What I said was if we set x equal to 0, we would have y squared equals negative 5, which is not a real number. So I can't set x equal to 0. I don't have any x-intercepts for this graph. So it would have to open sideways, because if it opened up and down, it would eventually have to hit the y-axis, and it cannot. But since it's the x squared term that's positive, it's going to open sideways. Okay. Now, center is 0, 0. A equals the square root of 7. That gives me how far it is from center to a vertex. And remember, the vertex is going to be just like it was for the parabolas. It's the where the parabola opens from, okay? Or the hyperbola in this case. So our vertices here are plus or minus the square root of 7, 0. Foci, remember this is our major or transverse axis. A focus is square root of 12 or 2 square roots of 3 units away from center. So that will be plus or minus 2 square roots of 3, 0 for your focus. Let's see, 2 square roots of 3 is what? Approximately it's going to be a little bit less than 4, so 3.4-ish. Okay, so this would be a focus. Now, just like it was with a parabola, your foci will always be inside the bowls of the two ends of your hyperbola. Now, here's what we do to get our graph. We're going to draw in the conjugate axis by starting at center and going B units up and B units down. So we're going to have 2 square root of 5 here and here. So here's my conjugate axis. Now we're going to draw a box where we draw the box having the midpoints of the side of the box are the endpoints of the conjugate axis and the vertices of your hyperbola. Okay, so let me say that one more time. I drew in the conjugate axis. The top point of my conjugate axis in this case is 0 square root of 5. The bottom point is 0 negative square root of 5. I already know the vertices are here and here at plus or minus square root of 7 and 0. These 4 points need to be the midpoints of the sides of a rectangle. When you draw that, the diagonals of that rectangle will be your asymptotes. So I'm going to draw in the diagonals of those rectangles right here. Remember, diagonals just go from corner to corner. Okay. That pair of lines represent my slant asymptotes. And so when I draw this graph in, the further we go to the right, the closer we get to those slanted lines. So we're going to go closer and closer out this way, closer and closer out this way, and the same going this direction and this direction. Okay, now what are the equations of my asymptotes? Well, it's y equals, just think about it. What's the slope of this line? It's rise over run, which is b over a. So it would be plus or minus the square root of 5 over the square root of 7. Or plus or minus square root of 5/7 if you prefer. And that's the slope. So the equation would be plus or minus square root of 5/7 times x.
So why are the asymptotes important?
Well, if you want a graph of a function that has an asymptote, you always need to know what that asymptote looks like, yeah?
Right. But like, so are these just going to be like drawing these?
Well, it depends. You know, the hyperbolic trig functions, if you'll think back to when we talked about those, the hyperbolic trig functions are defined based on the graph of a hyperbola. And so they do have more than just, you know, a passing interest in applications as well. we're just trying to get the definitions right this minute. But, you know, one of the things, and I know that this is not an example of where you might need the asymptotes, but one thing that can often be modeled using half of a hyperbola is kind of the sway in things like, telephone lines or electrical lines. I think they even talk about the cables that support like the Golden Gate Bridge kind of stuff. Can often be modeled by hyperbolic graphs. Ellipses, you can talk about a lot of times orbits of planets may be represented by an elliptical type of a model. So there's lots of places we're going to be able to use them, but at this point we're really just trying to get down what those definitions are. So for us at this moment, we need to know it so we'll know how wide or how narrow to make that graph. Does that make sense?
Yes.
Okay. All right. So I know there's a lot in what we've just talked about, but if you'll notice, the things that we talked about with hyperbolas and ellipses are very similar. A, B, and C represent the same things pretty much for an ellipse that they do for a hyperbola. A is always the distance from center to vertex. C is always the distance from center to focus. And B is the distance from center to the endpoint of the minor axis. It's just that for a hyperbola, sometimes we call that the conjugate axis. It just depends. So if you'll just practice with the definitions, I don't think that these will be too terrible to do really well on the final. Because one thing you want to keep in mind is since chapter 12 has not been tested yet, you'll have more questions over chapter 12 on the final than you would normally. You know, if we had already had a test over chapter 12, you might not have, but a couple questions. But with it being brand new material as far as testing is concerned, you'll probably have 3 or 4 questions from chapter 12 on your final. All right, so what if we go the other way and I give you some information and ask you to find me an equation of a hyperbola? So for example, I want you to find an equation of the hyperbola with foci at -13, 0 and 13, 0, and vertices at 12, 0 and -12, 0. Okay. When they give me information like this and I'm asked to find the equation, usually what I do is I try to draw it out so I can think about it a little bit. I have a focus at 13, 0. So I'm going to call this 13, 0 and -13, 0. I have a vertex at 12 and at -12. So what has to be the center of this hyperbola? What's smack dab in the middle of those 4 points?
0, 0.
0, 0. The center's always going to be halfway between your foci and halfway between your vertices. In this case, the center is 0, 0. So we either have something like x squared over a squared minus y squared over b squared equals 1, or we have something like y squared over a squared minus x squared over b squared equals 1. Which one do I have to have in this case? Which one? I'm sorry.
The x squared.
Yeah, it's got to be this one, because remember, these are the ones that open sideways. Anytime you have a horizontal transverse axis, it's kind of, remember, it's the equivalent to the major axis for an ellipse, and we may call it the major axis depending on who you're talking to. So when you have a horizontal major axis or transverse axis, it's always going to be x squared over a squared. Okay. So if I could just figure out what A and B are, I would be done. Well, A is always the center to vertex distance. So this distance right here is A. The distance from center to focus is always C. So I know from what they told me that A is 12 and C is 13. So I need to figure out what B is. Well, we know C squared is equal to A squared plus B squared for hyperbola. So we would have 13 squared is equal to 12 squared plus B squared, or B squared is 169 minus 144, which is 25. So B will be 5. Just plug in A and B and we get the equation x squared over 144, which is 12 squared, minus y squared over 25 is equal to 1. Pretty cool, huh? Any questions? All right. What if we want to find the equation of an ellipse? And if you are still here with me, I need you to type here in the chat. Okay. The ellipse has a center at the origin. Major axis is horizontal. With length 12. That doesn't look right. Length 12 and a minor axis of length 6. So can anybody tell me what A and B are immediately from just the information that I have given you right there?
6 and 3.
6 and 3. You're done with that part, right? We're talking about an ellipse. So now we need to figure out, is it x squared over a squared plus y squared over b squared equals 1? Or is it y squared over a squared plus x squared over b squared equals 1? That depends on the major axis. Since the major axis is horizontal, it's wider than it is tall, so it'll be this form. When it's wider than it is tall, the a squared is under the x squared. So we just have x squared over 36 plus y squared over 9 is equal to 1. And it's as easy as that. Well, I say easy. That's all relative, I recognize. But if you know your definitions, that part is not too bad, right? All right, so that is the last section of Cal 2. Yay for you. So before Wednesday, do your homework for section 12.4 and anything that you haven't done up to that point. So be ready to ask any homework questions and come prepared to ask questions about your final, because that's our final exam review day. And then your final is a week from today from 12:30 to 2:30, but I will open it at 12 just so you can start at your regular time if you want to. Any questions?
Just a quick clarification question. So you got A equals 6 by dividing 12 by 2?
Yeah, because the major axis length is always 2A.
Awesome, thank you.
Yeah, and if you're looking at the axis between your vertices on a hyperbola, it's also always 2a. And so anyway, it's always half the distance of, or half the length of the major axis is going to be a. All right. Anything else?
So
whenever we're all done with this, can you pull back up the hyperbola and no, excuse me.
That?
Yeah.
Okay.
That and the ellipse sheet so I can finish copying it down. I didn't quite finish it.
You bet. There's the hyperbola. Just let me know when you're done, and then I'll move it to the ellipse.
Thank you.
You bet.
So Wednesday is just going to be a review day.
Wednesday is a review day for your final. Yes.
Would you be able to have another review day for like how we've been doing for the tests, like 8 p.m. on another day?
I'm exhausted.
Okay, I understand.
Let me
That's
think about it. Let me look at my calendar and see if we could work one in. But that kind of makes me feel like you're asking if you have permission to not be ready to review on Wednesday.
Well, no, it's just I work the rest of the day tomorrow, and so I don't know if I'll have time to do any of the review questions.
I gotcha. Well, let me look and see what I've got down this week, and I will definitely consider it, and I'll let you know on Wednesday.
Sounds good. Thank you.
You bet. Anything else? All right. So if you're finished copying down for the hyperbola stuff and you want to go, I will talk to you on Wednesday. And if you want to stick around and if there's anything else you want to copy down, just let me know. And I will put up, was it ellipses next, Glenn?
Yes.
Okay.
But I'm still not finished copying.
Okay, that's fine. Just let me know.
When he's done with that, could you do an example, like a real life example? Like I was going through the homework for this section. There was one about a bridge.
Okay.
Could you just do something similar? It doesn't have to be a bridge. It could be like a real world application, I guess.
And I did post these two in your, I think announcements maybe. Are you ready for ellipses, Glenn? Are you
No, sorry. I actually just had to take a work call, so I had to deal with that
Okay.
right quick.
Well, I'm going to go ahead and answer his question then.
Yeah, that's
Um,
fine.
And then
Uh,
if you want, I will upload this on YouTube today. So if you don't have time, if you need to, go to work or whatever, you can copy them down off of the YouTube video if that would make it more convenient for you. All right. So you wanted an example like okay. It says the cables of, this is from like your last homework question type. It says that, for example, the cables of a suspension bridge, and it shows it. Can be modeled by a parabola. And in this case, they just tell us it's a parabolic shape. Okay. The towers supporting the cable are 1,200 feet apart. So if this tower and this tower, they are 1,200 feet apart and 120 feet high. So this would be 120 feet. And so would this one. The cables touch the road surface midway through. So our vertex is just at road surface. What's the height of the cable at a point 300 feet from the center of the bridge? So if this is the center of the bridge, which is where it says the cables touch the road, we want to figure out how high the cable is off the road 300 feet away from center. Okay, we all good? So we just need to find an equation for this parabola. So since the way we have it drawn, I have the vertex at 0, 0. We know we have something of the form y equals ax squared, because if the vertex is 0, 0, then B and C are going to have to be 0. Okay. Let's see, what do we know? Well, this point, for example, would be the point where X is 600, because it's half of the distance between the two towers, and Y is 120. So one point on the graph of this parabola would be 600, 120. So just plug it in. And solve for A. Right. So what do we get there? 120. So I get A is 1/3000 in this particular case. So my equation is y equals 1/3000 x squared. And you want to know what this y, or vertical height, is when x is 300. Just plug it in. So we'd have y at 300 would be 1/3000 times 300 squared. And I get 30. Is that kind of what you wanted to see?
Yes.
Okay. Typically on one like that, you're just going to have to find a formula for whatever's being modeled. Like in this case, it was a parabola, or if it was elliptical or whatever, and then answer the question based on the graph or the picture that you've been given or drawn.
All right. Thank you, Professor. That was it for me.
All right. Anything else, Jennifer, or either one of you? If you have anything else, I'd be happy to answer.
Yes, ma'am. It was over our last homework. It was just one section. It was on question number 4.
Okay.
I was understanding everything as we were going through our lecture that day, but for some odd reason, when I got down to the homework, I just completely forgot, and I tried to look through our notes and stuff, and it just didn't make sense to me. So when we're looking at our R values, you said something about A mattering when you're choosing.
Are you talking about number 4 on the homework?
I'm talking, I think it is, because it does matter what your R values are. Like usually you have 0 and then pi over 2, pi or 3 pi over 2 and 2 pi. But
Right.
yeah, but what I'm saying is that sometimes it changes based on what you have. Does that make
It changes if you change the period of the function. The period of this function is not changed. So your key points would still be 0, pi over 2, pi, 3 pi over 2, and 2 pi.
Okay, what if it was...
But if you had like R equals 3 sine 2 theta or something like that, the key points occur at quarter points of the period. The period for this function is 2 pi over 2, which is pi. Okay, you always take 2 pi over whatever that number is right there. For sine and cosine, that is. So quarter points of that would be pi over 4 is how far they would be between them. So you'd start at 0, then you'd go pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and so on and so forth.
So you're dividing by, so you're taking 2 pi and dividing with whatever you have.
You take the period and divide by this coefficient to get the period of the new function.
Okay.
And
Would it-
then the key points are 1/4 of the period apart. So you start at 0 and go 1/4 of the period each time.
Okay, what if it was 3?
What if what was 3?
What if the period was 3?
So you're telling me you've got R equals 3 sine of, let's see, 3 over 2 pi. So you've got a function like that.
Okay.
Then the period there would be 3. And so quarter points of your period, you'd go 0, 1/4 of 3 is 3/4. So you go 0, 3/4, 6/4, 9/4, 12/4, and so on and so forth.
Okay. All right. Thank you.
You are, did that answer your question? Or were you wanting it to be like a period of 3 pi or so? Or were you wanting a 3 in here?
Well, I am still confused. It's just, I just don't really understand. Like, I remember, I understood it when we were going over our lecture. I just don't understand it anymore. Like, it's...
Have you rewatched the lecture?
No, I haven't. I probably will just go.
I'm not really sure I know which part your question is, but if you have something like R equals A sine B theta or cosine, it could be either one. The period of that function will always be 2 pi over B.
Okay.
And your key points start at 0, since we're not shifting right or left or anything like that. And then you add 1/4 of the period. So it'd be 0 plus 1/4 of 2 pi over B plus another 1/4. So you take this one, you add 1/4 of the period. To get to this one, you'd add another 1/4 of the period. And so on and so forth. So let's say you had R equals 2 sine 6 theta. What's the period of that function?
2 pi over 6. So
Correct.
pi over 3.
Yes. So if we were graphing this in rectangular coordinates, we would get the whole graph between 0 and pi over 3. We don't get the whole graph in polar coordinates in one period. We just get basically the equivalent of two petals. And this one would have 12 petals if we were drawing them all out. But to get started on it, you would start at 0. And we're going to add 1/4 of the period. 1/4 of pi over 3 would be pi over 12. To get to the next key point, you're going to add another pi over 12, so that'll be 2 pi over 12. Then 3 pi over 12, and so on and so forth. What's cool about the key points is these are the points that when you plug those in here, you'll end up taking the sign of 0, sine of pi over 2, sine of pi, sine of 3 pi over 2, and sine of 2 pi. That's what's special about these, is that when you plug them in, you get the high points, low points, and midpoints.
Okay. I think I got it.
Okay. Let me know though, and remember, I've still got lots of office hours, so if you're still stuck after you work on it a little bit more, let me know and meet me in Zoom or something.
Okay. Tomorrow my classes are back to back.
Okay. Well, if you can't, just shoot me an email and we'll get it done.
Okay. Thank you so much, ma'am.
You're welcome. Bye-bye.
Wednesday. Bye-bye.